Start.
Describing the semiempirical binding energy or mass formula, we have considered several terms. There is the volume effect, Coulomb energy, surface energy, symmetry effects, and the pairing energy. Now, and the finite feature of the nuclear forces are ignored here. Now, so this is the 5 terms. This is the binding energy formula. Now, the standard binding energy formula may be written in this form, where the atomic mass is described by this equation. Now, if one puts the expression of this binding energy from equation 1 in equation 2, then one gets this one, equation number 3. Now, the equation number 3, after some algebraic manipulation, one may rewrite this equation, equation 3, in the form that we collect the terms containing A, containing Z and Z square, and A and Z independent terms, then one gets the equation as this one, that M Z A C square, C is multiplied in this side, then you get Z mass of the proton plus A minus Z mass of the neutron. C square minus CDA plus CD CCZ square Coulomb energy term, A to the power minus 2/3 plus CA to the power 2/3 plus this term CS A inverse A minus 2Z whole square minus plus delta by 2. Now, if we combine these terms, that is, if we break this square and collect the terms containing A or Z square or Z, then in that case, one gets the equation that MZA C square is equal to MN C square minus CV plus CS plus TA A to the power minus 1/3 multiplied by A plus MPC square minus MNC square, MPC square minus MNC square minus 4CS into Z and another term containing Z square plus CCA to the power minus 1/3 plus 4CS A inverse z square minus plus delta y twice a. Okay. This is the equation. That is, if we write if we say this is x, this is y, this is small z, then we write it x into a plus y z plus z square minus plus delta y twice. And this is your y, this is your z. So we get the equation of a general parabola. This is a parabolic equation. Now if we plot the atomic mass or binding energy versus the atomic number z, then we get a parabola. Now this is equation of a parabola. So therefore this binding energy formula, this contains several constants or parameters. The plot of atomic mass m, the plot of atomic mass m versus the atomic number gives a mass parabola. The minimum of this is a parabola. If we plot like this, binding energy or mass and versus z, then we get parabola. So the minimum of the mass occurs, suppose say for z is equal to z, suppose this point is z. Now therefore minimum of this mass occurs at z, so we differentiate this equation with respect to z, and what we get? Now therefore differentiating the above equation, with respect to z, then what we get? Del z of say mc square, m is zs square obviously, then what we get? That is y plus twice z into z, and which will be equal to 0 because the minimum point for z is equal to z, right? Now therefore, or you may write say when z is equal to z, only this will be equal to 0. So better to write here say z a, that is for when z is equal to z. Now therefore from this one gets the z is equal to minus y by 2z minus y by twice z. And now if we substitute the values of y and z from the equation, therefore we get, what is the value of y? That is, you get mp minus mm c square minus 4cs and here you get twice CCA to the power 1/3 plus 4CS A inverse. Now, here it contains Mp minus Mn square. The mass difference between the proton and neutron, which is very very small compared to this term. So therefore, if we neglect this term as it is Mt minus Mn square is very small, then what we get? That is J day is equal to 4CS divided by this term, or say you write say twice CS, CCA to the power 1/3 plus 4CS A inverse. Or it may be simplified to write A by 2 1 plus CC by 4 CS A to the power 2/3 inverse. So J day is the region of mass stability. J day is the region of mass stability. But need not be an integer. J day may not be an integer. Okay. So this defines the region of the mass stability. Now the value of the constants in equations 1 and 3, which we have written earlier, that are determined, they are actually constants or parameters. They are determined from the theoretical calculations or by adjustment to fit the actual mass or the binding energy of a particular nuclide. Suppose if we consider we know that the actual mass of a particular atom or say binding energy of that nuclei, then what will be the value of this Cc, Cs, Av or As like that? They are determined from the theoretical calculations or adjustment of these parameters. Their parameters are adjusted in such a way so that the proper binding energy or the atomic masses comes out. So these are the parameter fittings. So these parameters are fitted or adjusted. The value of the constants, in the binding energy formula or the mass formula is determined by a combination of theoretical calculations and adjustments to fit experimental values Now these values are the value which are obtained. I am just mentioning here the values. These values are CV equal to 14 MeV, 14 MeV, CC 0.146 MeV, CS is 19.4 MeV, CA is 13.1 MeV, and the pairing energy term delta is equal to minus 270 MeV for even jet nuclei, and it is 0 for odd A. Either say Z may be odd or N may be odd. When A is odd, the pairing energy term is 0, and this is plus 270 MeV for even A, but they want Z. So these are the parameters fitted to find the exact experimental value of the or mass of the atom, particular atoms, or the binding energy of that nuclei. Now, inserting all these values, if we insert all these values in the binding energy formula, so the inserting all these values, what we get? The binding energy of a particular nucleus is given by 14.0 A minus 0.146 Z square to the power minus 1/3 minus 13.1 A to the power 2/3 minus 19.4 A inverse A minus 2Z whole square minus E delta. Now, so this is the binding energy formula. So by substituting the value of different nucleides A and Z, one can find the binding energy of that particular nucleus. Now this formula, the semi-empirical binding energy or mass formula, generates quite effectively the binding energy or masses of a particular atom or nuclei. Now, what is the implication of this binding energy formula? Now the implication of this binding energy formula, that it gives you important or some idea about the stability of the nucleus. Now because if we draw the curve between the binding energy and the atomic number Z, we get a parabola. Then which one is the lowest point, the stability point? From that nuclei will be the most stable among the all isobars. Okay. Now the semi-empirical mass or binding energy formula, the semi-empirical mass or say binding energy formula it produces quite accurately the values for many nuclei but does not account for all of the features of the nuclear binding energy. It has certain demerits. It cannot account because we have not accounted for the finer features of the nuclei, but does not account for all of the features of the nuclear binding energy. Because we see later on that in the series of the binding energy formula or mass formula, there are certain discontinuities. Certainly there are certain nuclei for which the binding energy calculated or mass calculated by this formula differs from the experimental value by 1 or 2 MeV. So these discontinuities are there. We shall discuss later on that why these discontinuities or discrepancies arise. Now, the most important implication of this binding energy formula, that it gives the stability or helps us to study the stability of the different nucleus or different isobars. The binding energy formula helps account for some of the important features of stability properties of the nuclei. Now, it is observed that the pairs of stable isobars means our mass number is same, but Z may be different. Now, most of the stable isobars, it is observed that they differ in their atomic number by 2 units than by 1 unit. Suppose you have a one isobar, say, suppose say X, A, oh, it has a certain, okay. Suppose it has, say, value Z, and another is Y, Z plus 2. This will be very stable. So, it is observed that the stable isobars, they are generally differ in their atomic number by 2 units rather than 1. That is the Z plus 1. You get only a few exceptions are there, a few nuclei which with this difference, that the atomic number differs by 1 unit, they are stable. Most of the stable isobars, in that case, their atomic numbers will differ by 2 units rather than 1. Now, let us see why it happens. So, by semi-empirical mass formula, one can explain this stability of different nuclei. Now, the stable isobars generally differ in their atomic number by 2 units than by 1 unit. Now there are more than 60 isobaric pairs for which this delta Z is plus minus 2. But there are only 2 pairs, for which delta Z is plus minus 1. Okay. Now, generally there is a tendency that most of the stable isobars, they differ by in their atomic number by 2 units rather than 1 unit. There are exceptions, only 2 pairs are there. Now, so these are actually cadmium, say 48, 113, and another is indium 113, 49. And another is pair is SB 123, 51, and another one is P 123, 52. So these are the 2 pairs which are stable. You see their mass number, atomic number differs by 1 unit. Here also atomic number differs by 1 unit. So A equal to 113 and 123 are the 2 exceptions, but they are stable. Now, if we consider different cases, that is even a nuclei, odd a nuclei, and plot the graph. Now we consider the binding energy formula for a given odd A, or odd A. We consider a odd A nuclei and plot the binding energy graph versus the atomic number. Then what we get? Now for odd A, a nuclei, the odd even term, that is E delta, the odd even term vanishes. It will not be there. Because it is the value of E delta, delta is equal to 0 for odd even, for odd nuclei. The binding energy versus the Z curve, if we plot, will be a parabola, obviously, will be a parabola, because the equation is a parabola equation. Now, we consider the value of A. Suppose say A is equal to 73. Our value of A say is 73, say odd nuclei, and then if we plot the graph, then what we find? A equal to 73. Here, say binding energy, and in this side plot Z, and in this side is binding energy. This is 32. 31, 30, so this is 29, 33, now the most stable of this series here, we get this is germanium 73, 32. Then here we get gallium 31. Here we get zinc 30. Then here AS 33, 73, and here Zion 73, 34. When it comes from here to here, then it decay to this stable point by emitting the electron, and this comes from here to here and here to here. Either they emit say beta plus or say electron capture. Now the bottom of the card represents the most stable nuclei of this series, and other nuclei, that means it is the most stable, that means it has the lowest binding energy. in other words, you can say the greatest binding energy, the most tightly bound, and all other isobars which lie on the two arms of this parabola, they are the less binding energy than this one, because this is the most stable one, the highest binding energy. Now all the masses are larger than this one, it is the lowest mass, and so from this side this J comes to this liam by emitting an electron. Now here 30 number of protons are there. When the electron is emitted, that means proton plus electron, that gives another particles are there. We are not going to this, but crudely the charge is conserved, proton plus electron, that makes a neutron. So when the electron comes out from this nucleus, then what will Z will be increased by 1 unit. You see from here, electron is coming out, so Z is increased by 1 unit. Similarly here also, when the electron comes out, the Z is increased by 1 unit, so it goes to 32. Similarly from in this case, when it comes from here, Z equal to 34 to 33, that means the neutron is converting, okay, and positron is coming out. Now all the electron capture will take place here. The nucleus will capture an electron and electron will be captured, so that is mass will be reduced, atomic number will be reduced, because the proton will be converted in that case into a neutron, so its atomic number will be reduced by 1 unit. Similarly here also it will be reduced by 1 unit. So on this side, if the mass of this atom is larger than this one, then the electron emission will take place and they will come to the stable point. And on the other side, when if Z is larger and mass is larger, then in that case they will emit a positron or they will capture the electron to come to this stable point. Now the nuclides which lie on the two arms of the parabola either emit electron or positron, or by electron capture. Now, therefore, one can write that if the mass of the isobar is, if the mass of this isobar of Az, if it is greater than the mass of Az plus 1, that is on this side, mass of this Az is greater than the mass of Az plus 1. 30 zinc has the larger mass than the Z equal to 31. Then in that case, what will emit? Electron emission will take place. Then in that case, the beta minus emission, that is electron emission. And if mass of this nuclei is greater than mass of a z minus 1 plus twice mass of the 2 times the mass of the electron, then in that case you get say positron emission. Only positron emission, that means the mass of this will be larger than this by 2 times of the mass of the electron, then only the positron emission will take place. Otherwise, if it is only greater than this, then electron capture will take place. That means if the mass of Az is greater than mass of Az minus 1, then the electron capture. Naturally, question may arise in your mind that the dimension of the electron is much larger than the nucleus. Then how the electron or positron is emitted from the nucleus? Your nucleus is, electron is larger in size than the nucleus. Because the electron or positron emits from the nucleus, they are not within the nucleus, they don't exist within the nucleus, but they form, when they emit from the nucleus, they form at the surface. At the surface, the electrons and positrons are produced and they will come out. Because the dimension of the electron is much larger. Actually, in writing it is not like this. Actually, one may picture it in this way, that is, this is the nucleus and this is your electron or positron. Then the electron and positrons are actually formed at the surface of the nucleus and they will come out. So they don't exist within the nucleus. They cannot exist because if one can estimate the idea by the uncertainty principle, then one can prove that the electron cannot exist within the nucleus because its dimension is much larger than the nuclear dimension. Now, therefore, we have, that is, zinc 3073. It is on this side, left hand side of this. This mass is larger than this one. Ga 3173. So here you get electron emission, and finally it comes to germanium, the most stable one, 3273 by beta emission. And on the other hand, on the other parts, you get this 3473, either positron emission or say electron capture represented by kappa. You get is 3373, and finally it comes to this germanium. So the binding energy formula, semi-empirical binding energy formula, has the ability to explain the stability properties of the nuclei. Now we consider we have considered say odd A. Now we consider even A nuclei. Now for even A nuclei, even A nuclei, for even A nuclei, what we get? There are two cards. It is two parabola. One for even Z, even A. Even Z, even A. A is even, so even Z, even N maybe, and another for A is even, so Z may be odd, N may be odd, so A will be even. So it is for odd Z, even A. So we get, there are two possibilities. So we get two parabola, two cards. Now, if we draw the binding energy versus the atomic number for this even A nuclei, now then we get Z along the x-axis and here the binding energy along the y-axis. So you get the upper one is for odd even, odd Z, even A, and the lower one, this is for even, even. Because the even nuclei, you see, they will be more stable. That's why their binding energy is much larger. They go lower than this one. Now, if we consider the A equal to 64 in this case, suppose our A is equal to 64, then we plot, here we get now the lower one, here it is Cu64. Here you get nickel 64. Another here zinc, Z is equal to 30, zinc. And here you get say cobalt 64. And here you get Ga64. Now it comes from here to here. Now here the electron emission of here will take place, and here the positron emission. Here in this case, when the copper comes from here to here, it emits a positron, and here the electron. because it comes from Z29 to Z minus, it comes from Z29 to Z plus 1, zinc. Okay. So here electron emission and here say positron emission will take place, and the lower one which is for evening. So here for evening cases we get, that means for the stable isomers, you get two stable isomers here, and they are different. One is 28, another is 30. This is not more stable. Here nickel and zinc isomer same A, but one is 28, another is 30. Say delta Z is plus minus 2. The odd even nuclei, this one, the odd even nuclei lie on the upper star. And are unstable. With respect to those on lower terms. They are unstable compared to this, which are lying on the lower term. The result is that what we see that the copper is not very stable because it decays either into nickel or into zinc. So the result is that no stable odd Z even A, no stable odd Z even A nucleus should exist. The only exceptions to this rule are, what are the exceptions? So nitrogen 14, there is a odd Z is 7, but it is very stable. So your deuterium 1 proton and 2 neutrons are there. So there are exceptions. These exceptions are deuterium, lithium 6, Z is 3, boron 10, and nitrogen 14. These are the exceptions. Or in general, the odd Z even A nuclei are not stable. Now, so the nuclides with stable isomers, we have seen that zinc 6430 and nickel 28, 30, 64. They lie at the bottom, they are the most stable one. And from this it is clear that they differ by 2 units here, delta Z is equal to 2. Now therefore, the binding energy formula helps us to explain the stability of the different nuclei. Why say stable isomers are differ by Z is equal to P unit. Exceptions are there that we have discussed. These are the exceptions. It can say well explained that the stability properties of the nuclei. But there are certain drawbacks of this, because it is observed that there are certain when we calculate the binding energy of the different nucleus with the help of semi-empirical mass formula, then it is found that when the atomic number or the individual number of neutrons is equal to say Z or N equal to say 8, 20, 28, 50, 82, 50 or 82 or 126 and 124 and 184, either Z or N, because your Z cannot go beyond this or this. So either Z or N equal to 8, 20, 28, 50, 82, 126, 184, they are most stable because they are calculated binding energy by the semi-empirical mass formula, and their actual binding energy differs by 1 or 2 units. So there is a discontinuity at these points, because at this point with Z equal to 8 or N equal to 8, the oxygen 16 very stable, calcium 40 very stable. Their actual binding energy lies 1 or 2 MeV less than the actual calculated binding energy by the semi-empirical mass formula, and this happens due to the cell closure. In atomic physics, we know that there are some inert gases and they don't react with the other elements due to the cell closure. Here also, when the neutrons and protons are filling up in the nucleus, the cell closure comes at these values. So they are most stable, they are very tightly bound. That's why in the semi-empirical mass formula, that term is not there. So we have to consider the effect of the cell closure in the semi-empirical mass formula also. Okay. One more.